my research project was on METHI, which is the name of the model that I made, which is a machine learned exoplanetary habitability index. So to break this down very simply, what I did was that out of all the exoplanets that are currently found in today's world, I created a model that could assess its habitability to sustain life on that planet. So to start off with a little introduction, there's like a challenge that's going on with finding these habitable worlds. Right now, since 1990s, there have been over 5,500 confirmed exoplanets, and there's still thousands more that's awaiting these validations. But however, the problem with checking if these exoplanets are habitable or not is that there are very different planetary and stellar parameters you need to take into consideration. And then there are some existing like indexes like the ESI, PHI, and CEPHI. They're all there, currently used, but these ones are really relied on some like handcrafted formulas which people made themselves, and sometimes it misses like nonlinear relationships that we don't really see with our naked eye. So that's why I thought of implementing machine learning, because this could be something that not only can be used autonomously, and it'll be much more accessible in the future, because once we get a lot more planets, over thousands of planets and millions of methods. And also this is more feasible compared to people physically evaluating each individual planet. So if we want to go into the framework, I can basically bring everything down into 4 stages: the binary classification, then the unsupervised clustering, then habitability scoring, and then finally the public web interface. So this is like a small little, for the exoplanet archive source data set that's available to everybody. It shows all the current exoplanets found today. There we took right now the main 5 parameters that are used to assess habitability on some sort of exoplanet. And then these were these 5 parameters. And from there onwards, we started the first step, which was the binary classification. And then from the data set we had, we classified 4,064 as non-habitable and 75 as habitable. And then we moved on to the clustering stage, where we used the top 3 clustering methods. And from here, we wanted to assess which one would yield the most amount of results. We tested each of these clustering individually. And then we found that k-means with k equal 2 was the best cluster. And we saw that in cluster 0, there was 43 exoplanets, and in cluster 1, there was 32 exoplanets. And then we moved on to stage 3, which was the habitability scoring. And from here, these are the main 3, and then we saw out of all of this, the highest yielding was from the ensemble. And then with this model that we used, we found our results, and then we made a public accessible web interface. Now the forest. So the first stage is the binary classification. So once we extracted the data from the NASA Exoplanet Archive, like I said, we selected 5 critical parameters that are used for habitability, which right now are planetary radius, incident stellar flux, and then this was a small little formula that we combined using lots of previous methods and what we saw from ESI, PHI, and we saw that planets were labeled habitable if they were under these constraints. And we used the random forest classifier, and then this achieved a very exceptional score, which showed it that was pretty accurate. And that's how we classified out of the 4,139 planets, 75 planets, exoplanets, were classified as potentially habitable. And this is a small little confusion matrix that's basically showing you the true positives, the false negatives, and everything there. And then from that, we moved into the unsupervised clustering, which was the stage 2. And from the 75 habitable candidates, we applied 3 clustering algorithms, the k-means, GMM, and dbScan. And this was just like a quick little bar graph that you can see. And if you see at the bottom, the k-means with k equal 2 achieved the highest silhouette score. And because of this is the clustering method that we used. And using this k-means k equal 2, that the k equal 2 represents the amount of clusters there are, which is cluster 0 and cluster 1 in this case. And we found that cluster 0 comprised of 43 exoplanets and cluster 1 was 32. And then both of these clusters have their own features. Like for cluster 0, they're more analogous to Earth. They're more temperate planets, more cooler and dwarfs, compared to cluster 1, which are more larger super Earths and hotter worlds. And then from the unsupervised clustering came to the 3rd stage, which was the habitability scoring. So this was where we developed a scoring framework for the 75 exoplanets. And then, like I said, we used 4 different regressors. And then with these 4 regressors, we wanted to evaluate which was the best regressor. And then using that, we wanted to compare it with how well our model performs. Like you can see here, the R squared, you can see the RMSE and the MAE. These we saw that out of all of these, the R squared for the ensemble regressor was the highest, and then also had the lowest RMSE and the MAE, which is the errors. So you would want those to be very, very low, and the R squared, you want them to be very high. And if you see, this is just a graph of the ensemble. You can see compared to the true habitability score versus the predicted score, which was in this case our model, it was pretty close to being accurate, which is around 0.9034. So this is the model we ended up using for the rest of the project, the ensemble model. And then from this model, we found, we made a list of like the top 10 promising exoplanets. And if you see, these were each of them like the 5 parameters that we talked about before. The HP represents the true habitability score, and then our ensemble habitability score. And this HP, if you're wondering where we get this NASA already has a certain amount of score dedicated for each exoplanet. And that's why we I trained my model, and I wanted to see how similar it was from the score. So in this case, you can see these ones are the most promising, and majority of them are very similar to their like actual true habitability score. And then stage 4 was where we used like a public interface. So now that we got the results, we found out that the best model was the ensemble model, and we saw that it had a very good accuracy with a 0.9, and it found good results. We wanted to have this into a way that more like we can streamline this so more people can use this. So in order to do this, I used Streamlit as a platform to build the METHI web application. It was a pretty simple application with a model layer, data layer, and an interface layer. And then this is kind of like an example. Like if I click this link, you'll be able to go over there, but this is how it would be, where you can see the top 10 most habitable exoplanets. You can search for an exoplanet that you want that might not be over there. And then you can see the certain score that we found using our model. You can see the score for that exoplanet. And also if they wanted to see like our just data set, they can always download our CSV. And then if you look at the advantages over traditional indexes that are happening right now, METHI really learns directly from the multidimensional data sets, which is why it's a machine learning, compared to like the traditional methods where they have not implemented ML, and it's been more like human-based, where people were directly like doing a cross-examination. And then it's a lot more interpretable because we have that Streamlit website that more people can accessibly use, compared to like other like ESI and PHI. They don't have any web interface where people can actually use and like implement that. Then is the extensibility, which is very useful because this can also move into biosignatures, which is also another method that we have not looked on now, but we are planning to look on in the future, which is just like how I said at the beginning, there were 5 certain parameters. Biosignature is like another parameter that's very new to what's happening right now in the field of astronomy and exoplanets. And this is something I'll also want to implement in the future. And it's very useful if we're using machine learning, because then it's very easy to just implement that next parameter. And then, like I said, the accessibility. And yeah, once again, unlike the ESI, PHI, and CEPHI, METHI really uses that machine learning, which is very important for this to become a more scalable project. And then finally, for the conclusions, like I said, the big key advancements was that METHI used machine learning. Found the ensemble model to be the best model, and that model had a very high promising score of a 0.9, which showed that it was pretty accurate compared to like the actual scores. Another thing is that METHI has that interface that people can always use, and it's very useful and very easy for it to become streamlined into the future because we're using machine learning and it can always be added onto. Now, like I said, for future directions, biosignatures is another new parameter that's coming up that's very easy to implement using what we have right now. And then AI-driven explanations. So this is something where we're thinking we could maybe even use some sort of like chat bots where people can physically ask them questions, like, you know, how we have our current Gemini, ChatGPT. They can, just like how we have on our Streamlit website currently, we could enhance this to make it more like user friendly, more easier for an everyday person to kind of understand. And then next is robotic telescope scheduling. So this is basically when more data is being acquired from, let's say, NASA, or let's think of like from the ESI or from any other space telescope in the world. As these new data is coming up, it can automatically be clustered into the machine learning model, which is something that could also be a future direction. I would say this experience is very useful because I kind of learned the entire process of starting a research project to like finishing and publishing in a journal. So in the future, definitely once I go to like university, grad school and everything, I kind of have like a framework already mapped up in my head. So I know that like, okay, I need to first develop, like do a literature review, first know what's happening in the background. Then I can actually implement my data, get results. And then from then on, I could actually publish it in a journal. I kind of know everything structured out. So I would think that's very nice. Overall testimonial, I think was really awesome. I feel like you guys did a great job to like really construct an entire research project in like, I think it was like maybe 2 months, something like that. And yeah, I feel like it was awesome.